We are going to build a microscopic picture of an ideal gas, and then watch that picture hand us back the macroscopic gas laws we already know. The goal of this chapter is a single bridge. From the motion of individual molecules to the pressure, volume, and temperature we actually measure. The promise is simple. We treat a gas as a huge swarm of tiny elastic particles. From their collisions with the Waals, pressure will fall out. From their average kinetic energy, temperature will fall out. And by the end, we will have not just the gas laws, but the full distribution of molecular speeds and the rule that connects a molecule's degrees of freedom to the heat it stores. Everything later, from heat engines to entropy, will sit on top of these identities. So whenever a symbol starts to feel abstract, come back to this idea. Pressure and temperature are not new physics. They are averages taken over an enormous number of molecular impacts. Before we do any algebra, we have to be honest about the model. Kinetic theory is not a theory of every gas. It is a theory of an idealized gas, and every idealization will eventually break. So let us list the assumptions we will lean on for the entire chapter. First, a gas is a huge number of identical, perfectly elastic point mass molecules. Second, the molecules are so small that their own size is negligible compared to the typical separation between them, on the order of 10 to the minus 9 meters. Third, the molecules move randomly in all directions, with speeds ranging from 0 to very large. Fourth, between collisions no intermolecular force acts, so no attraction and no repulsion. Fifth, gravity is irrelevant, because molecular masses are far too small for it to matter. Sixth, we will talk a lot about the mean free path, the average distance a molecule travels between successive collisions. And seventh, density is uniform throughout the vessel. Every one of these is a simplification. The places where they fail, real gases, liquids, dense plasmas, are exactly the places where our equations will need to be patched. We will see that most clearly with the van der Waals correction later in the chapter. Now to the first empirical law, Boyle's law. At constant temperature, the pressure and volume of a fixed mass of gas are inversely related. The product P times V is a constant, so if I double the pressure, the volume halves. The graph is the classic hyperbolic curve, falling steeply as pressure rises and approaching both axes without ever quite touching them. The physical reading is straightforward. If I squeeze the gas into a smaller volume, the molecules do not get faster on average, the temperature is fixed. But the wall is closer, so each molecule hits it more often per unit area. More impacts per second at the same momentum per impact means more pressure. The constant PV is the bookkeeping statement that those two effects exactly cancel. Boyle's law, then, is not really a law of gases. It is a law of counting wall impacts. Charles' law is the next step. At constant pressure, the volume of a fixed mass of gas grows linearly with absolute temperature. If I plot volume against temperature in Celsius, I get a straight line through the volume V0 at 0 degrees Celsius, and the line extrapolates downward, vanishing at minus 273.15 degrees Celsius. That temperature is absolute zero, and it is not measured directly. It is defined by where the linear fit crosses zero. In equation form, V1 over T1 equals V2 over T2, and in Celsius, V sub T equals V0 times 1 plus T divided by 273.15. Notice two things. The proportionality is with absolute temperature in Kelvin, not with Celsius. And the constant 273.15 is the slope of that line, an experimental number that turns out to be the same for every gas. That is why the Kelvin scale is not arbitrary. It is the scale on which the gas laws are linear. Gay-Lussac's law, sometimes called Regnault's law, completes the trio. At constant volume, the pressure grows linearly with absolute temperature. The pressure-temperature graph looks just like Charles' law, a straight line through the pressure P0 at 0 Celsius, extrapolating back to 0 at minus 273.15 degrees Celsius. So if I keep the volume fixed and double the absolute temperature, I double the pressure. The common trap here is to write P as proportional to the Celsius temperature T. It is not. The proportionality is only with absolute temperature T in Kelvin. The 1 over 273.15 factor that appears in the Celsius form is in fact the experimental basis for the entire Kelvin scale. It is the slope we measured, and from it we built the absolute zero that Charles' law also demands. Let us pull the three laws together. Boyle's law holds temperature fixed and says volume is proportional to 1 over pressure. Charles' law holds pressure fixed and says volume is proportional to temperature. Gay-Lussac's law holds volume fixed and says pressure is proportional to temperature. Each one fixes a different variable and turns the gas law into a simple proportionality, but notice the common thread. In every case, the proportionality is with absolute temperature. The gas laws are not really three laws. They are three shadows of a single statement. That temperature is the molecular scale quantity the gas is linear in. Kinetic theory is going to give that statement a quantitative form. Before we move on, a quick self-check. If I double the absolute temperature of a fixed mass of gas at constant pressure, by what factor does the volume change? And if I double the pressure of a fixed mass at constant temperature, what happens to the density? We will need both answers repeatedly in the next deck. The three laws we have so far all keep something fixed. Avogadro's law finishes the set by fixing the gas itself, not its conditions. Equal volumes of different gases at the same temperature and pressure contain equal numbers of molecules. So if volume, temperature, and pressure are matched, then the number of molecules N1 and N2 are equal. Out of this simple statement comes one of the most useful numbers in all of physics, Avogadro's number, N sub A, 6.023 times 10 to the 23rd per gram mole. And from it comes the molar volume at standard temperature and pressure. At T equals 273 Kelvin and P equals 1 atmosphere, every ideal gas occupies 22.4 liters per mole. That 22.4 is not a magic constant. It is the volume that holds exactly n sub-molecules when each one has the same average kinetic energy and the same pressure on the walls. Whenever you see 22.4 liters, picture that swarm, 6.023 times 10 to the 23rd molecules, all sharing the same thermal energy. Once we mix gases, we need Dalton's law of partial pressures. The total pressure of a non-reacting gas mixture is just the sum of the partial pressures. Each partial pressure is what gas I would exert alone in the same volume and at the same temperature. So P equals P1 plus P2 plus P3 and so on. The law holds when the gases are ideal, that is, when there is no attraction between unlike molecules, and when every component sees the same volume. It breaks down for strongly interacting mixtures at high pressure. The application worth remembering is humid air. The partial pressure of water vapor sets the dew point, and the partial pressure of oxygen is what your lungs actually care about. Two physically different questions, two partial pressures, one total pressure. The bookkeeping stays clean because each gas is independent of the others. Now we can unify everything into a single equation. PV equals nRT, that is the ideal gas equation, and it is the master combination of the chapter. Pressure times volume on the left, moles times the gas constant times absolute temperature on the right. The symbol table is worth a slow read. P is pressure, 1.013 times 10 to the 5th pascals at 1 atmosphere. V is volume, 22.4 liters per mole at standard temperature and pressure. N is the number of moles. T is absolute temperature, 273 Kelvin at standard temperature and pressure. And R is the universal gas constant, 8.31 joules per mole per Kelvin. The power of this single equation is that it reproduces every law we have met. At fixed T and N, V is proportional to 1 over P, which is Boyle. At fixed P and N, V is proportional to T, which is Charles. At fixed V and N, P is proportional to T, which is Gay-Lussac. And at fixed P and T, V is proportional to N, which is Avogadro. The four classical laws are not independent statements. They are four shadows of one equation. The constant R deserves a closer look. R is 8.31 joules per mole per Kelvin. It is the bridge between energy units on one side and per mole per Kelvin units on the other. We will meet R many times in this chapter, and the form it takes depends on the scale we are working at. Per mole, the gas constant is R itself. Per molecule, the right constant is Boltzmann's constant, K sub B, which equals R divided by N sub A, roughly 1.38 times 10 to the minus 23 joules per Kelvin. The two are not different physics. They are the same physics at two different scales, per mole versus per molecule. The conversion factor between them is exactly Avogadro's number, the number of molecules in a mole. So whenever an equation is written with K sub B, it is a per molecule statement. Whenever it is written with R, it is a per mole statement. Pick the scale that matches the question and the algebra stays clean. The ideal gas equation is wonderfully simple, and it fails in exactly the regimes where a real gas is most different from an ideal one. Two effects cause the failure. First, intermolecular attraction. A molecule heading toward a wall is pulled back by its neighbors, so it hits the wall with reduced momentum. The measured pressure is therefore lower than the ideal prediction. Second, finite molecular volume. The molecules themselves take up space, so the free space available for motion is V minus NB, not V. Both effects grow with density, so they matter most at high pressure and low temperature. The simplest two-constant correction is the van der Waals equation. The pressure term is increased by A over V squared, the volume term is decreased by B, and the product equals RT. The constant A measures the strength of intermolecular attraction and pushes the pressure up to compensate. The constant B measures the finite volume of the molecules and shrinks the available volume. Notice how A over V squared depends on volume. The correction is largest when molecules are crowded, exactly when the ideal equation is most wrong. It can sound paradoxical that van der Waals works at high pressure and low temperature, since that is the hardest regime to model. But it works there precisely because the two effects it patches are largest there. The van der Waals constants have well-defined units, and tracking them is part of using the equation correctly. The constant A has units of Newton meters to the fourth, or equivalently, kilograms times meters to the fifth divided by seconds squared. It carries the dimensions of energy times volume squared, because the pressure correction A over V squared must come out in pascals. The constant B has units of cubic meters. It is an excluded volume per mole, the volume that 1 mole of molecules physically cannot share. The range of validity of van der Waals is exactly the regime where the ideal gas equation fails most, high pressure and low temperature, where the two corrections matter. The equation still struggles quantitatively near the condensation curve, where the gas is turning into a liquid. For a precise fit there, you reach for a virial expansion or a more sophisticated cubic equation of state. But for now, two numbers, A and B, lift the ideal gas equation into the real world. We will meet them again at the very end of the chapter, when we define the critical constants T sub C, P sub C, and V sub C in terms of A and B. With that bridge in place, we are ready to derive pressure from the molecular picture itself, rather than assume it from experiment. Now we replace the empirical law with a derivation. Pressure is not assumed. It is built from molecular impacts. Consider a single molecule of mass m moving with speed v straight toward a wall. It hits the wall and bounces back elastically, so its momentum reverses. The change in momentum per impact is delta p equals 2mv between two successive hits on the same wall. In a cubic box of side L, the molecule has to travel to the opposite wall and back, a round trip of 2L. So the time between hits is delta t equals 2L over V. The average force from this one molecule on the wall is F equals delta P over delta T, which simplifies to mv squared over L. Now sum over all n molecules in the box and divide by the wall area L squared. The pressure is P equals the total force divided by L squared, which gives P equals m times the sum of V sub I squared divided by V. Or written more compactly, P equals mn over V times the mean of V squared. The picture is unambiguous. Pressure is momentum delivered per unit area per unit time. That is the simplest macroscopic consequence of microscopic impacts. The average that appears in the pressure formula is not the mean speed. It is the mean of V squared, the root mean square speed. We define V bar squared as the arithmetic average of V1 squared, V2 squared, all the way to V sub n squared divided by n. And we define the root mean square speed V sub RMS as the square root of that mean. Why the RMS and not the plain average? Because the formula for pressure contains mv squared, not mv. The quantity that gets averaged is the square of the speed, and the square root is taken at the end. Squaring weights fast molecules heavily, and that is exactly the weighting we want. The molecules that hit hardest are the fast ones, and they should pull the average up. So whenever pressure, energy, or temperature is in view, the relevant average is the RMS, not the ordinary mean. Two equivalent forms of the kinetic theory pressure formula are useful in different situations. The first is P equals 1/3 times mn over V times V bar squared. The second is P equals 1/3 times rho times V bar squared, where rho equals mn over V is the mass density. Use the rho form when density is the natural variable, the kind that comes out of a flow problem or a tabulated gas property. Use the mn over V form when you know the molecular mass, the number of molecules, and the volume separately. The factor of 1/3 is the fingerprint of randomness. Pressure depends on the component of velocity perpendicular to the wall, and on average, only 1/3 of V squared points along any given axis. The motion is isotropic, so the mean of V sub x squared, the mean of V sub y squared, and the mean of V sub z squared are all equal, each one 1/3 of the total mean of V squared. If the molecules streamed in a single direction instead, the factor would change. The 1/3 is a direct signature of disorder. There is a second way to read the same equation, and it is one of the most useful identities in the chapter. The kinetic energy per unit volume of the gas is E equals 1/2 rho times V bar squared, since each molecule contributes 1/2 mv squared on average. Substituting into P equals 1/3 rho V bar squared gives P equals 2/3 E. Pressure is 2/3 of the kinetic energy density. The numerical factor 2/3 is universal. It links a purely mechanical quantity, pressure, to a purely energetic one, kinetic energy per unit volume, for any gas of structureless molecules. Whenever you see P equals 2/3 E, picture a swarm of molecules in a box. Their total kinetic energy per unit volume, multiplied by 2/3, is exactly the force per unit area that the swarm exerts on every wall. Let us read the pressure formula line by line to see what controls P. Fix V and T. Vary the total mass Mn. And pressure is proportional to M, and more mass in the same volume at the same temperature means more pressure. Fix Mn and T, vary V, and pressure is proportional to 1/V. Having the volume doubles the pressure, which is Boyle's law again. Fix Mn and V, vary the temperature T, and pressure is proportional to T. This last row is the bridge to thermodynamics. The mean of V squared is not independent of T, it grows with T, and that is the content of the next slide. The common trap is to read pressure proportional to mass as a statement about different gases. It is not. It is a statement about the same gas at fixed V and T. If I switch to a heavier species at the same V and T, the pressure is the same because heavier molecules move more slowly on average. Mass and speed conspire to keep the energy per molecule fixed. We can now do the central identification of the chapter. Set P equals 2/3 E next to PV equals NK sub BT, and the average molecular kinetic energy falls out. E per molecule equals 3/2 K sub Bt, with K sub B equal to R over N sub A, roughly 1.38 times 10 to the minus 23 joules per Kelvin. So temperature is, up to a constant of 3/2 K sub B, the average molecular kinetic energy. Heavier molecules at the same temperature move more slowly, because 1/2 mv squared equals 3/2 K sub Bt keeps the energy, not the speed, fixed. Lift the result to a per mole quantity by multiplying by Avogadro's number. And E per mole equals 3/2 RT, the two scales are paired. Per molecule, 3/2 K sub Bt, with the RMS speed V sub RMS equal to the square root of 3 K sub Bt over M. Per mole, 3/2 RT, with V sub RMS equal to the square root of 3 RT over M. The same physics, two scales. Choose K sub B and M when you are thinking about a single molecule. Choose R and M when you are thinking about a mole. The crosscheck confirms it. Combine P equals 1/3 rho V bar squared with P equals NK sub BT over V, and the same V sub RMS falls out. SQRT of 3K sub BT over M equal to SQRT of 3 RT over M. With the speed fixed in two equivalent ways, we are ready to look at the full distribution of molecular speeds, not just the RMS. A gas does not have a single speed. It has a whole distribution of speeds, and three characteristic numbers are used to summarize that distribution. The most probable speed V sub mp marks the peak of the distribution, the speed that the largest number of molecules happen to have. The mean speed V bar is the ordinary arithmetic average of all the molecular speeds. The root mean square speed V sub RMS is the square root of the average of V squared, and it is the one that connects to kinetic energy and to pressure. All three are different averages over the same underlying distribution, and that is exactly why they have different numerical values. If you only remember one of them, remember V sub RMS. It is the speed that appears in 1/2 mv sub RMS squared equals 3/2 K sub Bt, the bridge between mechanics and thermodynamics that we just built. Let us derive V sub RMS from the kinetic energy identity. 1/2 mv sub RMS squared equals 3/2 K sub Bt. So V sub RMS equals the square root of 3K sub Bt over M, or equivalently, the square root of 3 RT over M. The same identity can be rewritten using density. With ρ equal to Mn over V and PV equal to Nk sub Bt, the RMS speed becomes V sub RMS equal to the square root of 3P over ρ. The scaling laws are worth keeping in mind. At fixed composition, V sub RMS grows like the square root of the absolute temperature. At fixed temperature across different gases, V sub RMS scales like 1 over the square root of the molar mass m. So doubling the absolute temperature multiplies V sub RMS by the square root of 2, roughly 1.41. It does not double the speed. The square root is the signature of energy being proportional to V squared rather than V. The other two characteristic speeds come from the Maxwell-Boltzmann distribution itself. The peak of the distribution is at V sub mp equal to the square root of 2k sub bt over m, or the square root of 2RT over m. Averaging the magnitude of V over the distribution gives the mean speed V bar equal to the square root of 8k sub bt over pi m, or the square root of 8RT over pi m. The mean speed is the one to use when a quantity depends on speed itself rather than V squared. For example, the flux of molecules hitting a wall, which is 1/4 nV bar. The three speeds are not arbitrary. They are three different moments of the same distribution, and the profactors a and V equals the square root of a k sub bt over m fix them in place. V sub mp has profactor 2. V bar has profactor 8 over pi, roughly 2.546. V sub rms has profactor 3. So the three numbers square root of 2, square root of 8 over pi, and square root of 3 are not three independent physical predictions. They are three fixed points on a single curve. The three speeds have a rigid ordering that holds for any ideal gas at any temperature. V sub rms is greater than V bar, and V bar is greater than V sub mp. Set V sub mp to 1, and the mean speed is 1.128, while the RMS speed is 1.225. The reason is the way the averages are taken. The RMS squares the speed before averaging, which gives extra weight to the high-speed tail of the distribution. The mean and the most probable differ less, but the mean still picks up more of the tail than the peak does. The trap is to write V sub mp greater than V bar greater than V sub rms. The direction is easy to invert, but the ordering is fixed. Memorize the direction, because the next time you compare two of these numbers on a homework or an exam, the order will tell you which average is which. Let us work one example end to end. Hydrogen, with molar mass m equal to 2 times 10 to the minus 3 kilograms per mole, at T equal to 273 Kelvin and P equal to 1 atmosphere, normal temperature and pressure. Plug into V sub RMS equal to the square root of 3 RT over m. The numerator is 3 times 8.31 times 273, and the denominator is 2 times 10 to the minus 3. The result is roughly 1.84 kilometers per second. That is the root mean square speed of hydrogen at room temperature. For an order of magnitude check, the speed of sound in air at the same temperature is about 340 meters per second, a factor of 5 smaller. Gas molecules are genuinely fast. Their mean free path between collisions, which is the topic of the next deck, is tiny only because the molecules are also extremely dense, packed close together. Speed and density conspire to keep the gas at ordinary pressures. Now to the full distribution. Maxwell's law tells us the fraction of molecules with speeds between v and v plus dv. The formula is dn equals 4 pi n times m over 2 pi k sub bt, all to the 3 halves, times v squared times the exponential of minus mv squared over 2k sub bt times dv. Two pieces compete to set the shape. The v squared in front is the speed space volume factor 4 pi v squared dv. As v increases, more and more directions in velocity space point to that speed, so the geometric factor grows. The exponential is the Boltzmann suppression of high kinetic energies. As v increases, the exponent becomes more negative and the curve falls. The competition between those two effects creates a peak, and that peak sits at v sub mp, the most probable speed. Raising the temperature flattens the distribution and shifts the peak to the right. The area under the curve is always 1 because it has to count every molecule. So a hotter gas is not just faster, it is broader with a longer high-speed tail. That tail is exactly what makes chemical reactions, evaporation, and atmospheric escape possible. The final piece of the kinetic theory picture is equipartition. For a system in thermal equilibrium, energy is shared equally among all the degrees of freedom. Per molecule, each active degree of freedom carries 1/2 k sub bt on average. Per mole, each active degree of freedom carries 1/2 RT. Degrees of freedom are the independent ways a molecule can store energy. There are always 3 translational ones: the motion of the center of mass in 3-dimensional space. Linear molecules have 2 rotational ones, rotation about the 2 axes perpendicular to the bond. Nonlinear molecules have 3 rotational ones, and vibrations, when they are active, contribute 2 each, 1 kinetic and 1 potential, because a vibrating mode stores energy in both. The total thermal energy of n moles with F active degrees of freedom is U equals n times F over 2 RT. Equipartition is the rule that turns the question what is the temperature into the question what is the average energy per degree of freedom. We will use it in the next deck to predict the specific heats of monoatomic, diatomic, and polyatomic gases, and to see where the classical picture finally needs quantum corrections. Equipartition tells us energy, but it does not tell us how to count. To use it, we need to know how many degrees of freedom a molecule actually has. The general rule is F equals 3A minus R, where A is the number of atoms in the molecule and R is the number of independent constraints between them. The degrees of freedom are what every active mode of motion will contribute 1/2 K sub Bt to. The shape of a molecule, linear or bent, rigid or vibrating, sets F directly. 3 atoms in a line, like carbon dioxide, have 3 translational modes, 2 rotational modes about the axes perpendicular to the bond, and a number of vibrational modes. Each vibrational mode contributes 2, 1 kinetic and 1 potential. So for a rigid non-vibrating model, we set vibrations to 0. For monatomic gases like helium, neon, and argon, there is no rotation and no vibration, so F is just 3. For diatomic gases like hydrogen, oxygen, and nitrogen, treated as rigid, F is 5, 3 translations, and 2 rotations. For linear polyatomic gases like carbon dioxide and acetylene, the rigid count is 7. For nonlinear triatomic gases like water, the rigid count is 6, 3 translations, and 3 rotations. The trap is the low-temperature regime. The source treats nonlinear triatomics as having F equals 6, 3 translations, and 3 rotations, and that is the rigid classical answer used in introductory thermodynamics. Quantum corrections break it as the temperature falls and vibrations or rotations freeze out. Equipartition gives the total thermal energy of n moles of gas with F active degrees of freedom as U equals F over 2 nRT, which is F over 2 RT per mole. The energy per molecule is F over 2 K sub Bt, so U depends on temperature and on molecular structure. Same temperature, same number of moles, different F, different stored energy. Specific heats follow by differentiating with respect to temperature at constant volume. C sub V equals the partial of U with respect to T at fixed V, which gives F over 2R. At constant pressure, an extra term appears since the gas does work as it expands, and C sub P equals C sub V plus R, which is F over 2 plus 1 all times R. The ratio gamma equals C sub P over C sub V equals 1 plus 2 over F. The numbers fall out cleanly. For a monatomic gas with F equals 3, C sub V is 3 halves R, C sub P is 5 halves R, and gamma is 1.67. For a diatomic gas with F equals 5, C sub V is 5 halves R, C sub P is 7 halves R, and gamma is 1.40. For a nonlinear polyatomic gas with F equals 6, C sub V is 3R, C sub P is 4R, and gamma is 4/3, roughly 1.33. As F grows, gamma falls. More ways to store energy means a smaller temperature rise per joule of heat at constant pressure. The same formulas applied to common gases give a compact reference table. Monatomic gases have U equal to 3 halves RT, C sub V equal to 3 halves R, C sub P equal to 5 halves R, and gamma equal to 1.67. Diatomic and linear polyatomic gases have U equal to 5 halves RT, C sub V equal to 5 halves R, C sub P equal to 7 halves R, and gamma equal to 1.40. Nonlinear polyatomic gases have U equal to 3 RT, C sub V equal to 3R, C sub P equal to 4R, and gamma equal to 1.33. The equipartition rule also extends beyond gases. The classical Dulong-Petit law predicts that the molar specific heat of any solid is 3R, roughly 24.93 joules per mole per Kelvin, because each atom in the solid behaves like a three-dimensional harmonic oscillator with 6 degrees of freedom. For liquid water, the classical value is 9R, roughly 74.97 joules per mole per Kelvin. The trap to remember is that these are classical numbers. They break at low temperature, where quantum treatments like the Einstein and Debye models replace equipartition. Diamond near room temperature is the famous counterexample to Dulong-Petit. So the equipartition rule is a powerful first approximation, but not the final word. Now to a length that ties the microscopic picture back to transport. The mean free path lambda is the average distance a molecule travels between two successive collisions. The formula is lambda equal to K sub Bt over the square root of 2 times pi times sigma squared times p. The symbol sigma is the effective molecular diameter, so the collision cross-section is pi sigma squared. The factor of the square root of 2 corrects for the fact that the target molecules are not standing still. They are also moving, and a head-on relative speed is faster than either molecule's speed alone. The scaling laws are easy to remember. At fixed pressure, lambda grows linearly with temperature. At fixed temperature, lambda falls like 1 over p, so in air at standard temperature and pressure, lambda is about 10 to the minus 7 meters, a tenth of a micron, while the molecules themselves are about 10 to the minus 10 meters across. The molecules spend almost all their time in free flight. They collide rarely, and when they do, the encounter is brief. That gap between collision length and molecular size is what makes the gas behave as a dilute swarm of nearly independent particles. Brownian motion is the visible face of the molecular picture. Suspended microscopic particles, like pollen grains in water, jitter continuously under the eye. The jitter is caused by the unbalanced bombardment of the suspended particle by molecules of the surrounding fluid. On average, the impacts from all sides cancel. But at any instant, the particle is being struck a little harder on one side than another, and the imbalance moves it. Robert Brown observed this effect in 1827 for pollen grains in water, and at the time no one could explain it. The molecular kinetic theory explained it. Brownian motion is direct, visible proof that molecules are real, moving, and numerous. Einstein's 1905 quantitative theory of Brownian motion turned it into something measurable. By watching how far a suspended particle wanders in a given time, you can extract a diffusion coefficient, and from the diffusion coefficient you can estimate Avogadro's number. That was one of the earliest numerical estimates of n sub a, and it was the first time the molecular hypothesis produced a number that an experiment could check. The same stochastic process governs stock prices, diffusion, and random walks, and we will meet it again in a later video in the Fiscribe playlist. We close the chapter where the ideal gas picture finally fails for good, at the critical point. Above a critical temperature T sub C, no amount of pressure can liquefy the gas. The van der Waals equation gives the three critical constants in terms of a NB V sub C equals 3B P sub C equals A over 27B squared. T sub C equals A to over 27 RB. The remarkable thing is a universal number that comes out of the algebra, the same for every gas. RT sub C over P sub C V sub C equals 8/3. That is the critical coefficient, a dimensionless combination of the critical constants, and it is fixed by the van der Waals model alone. Physically, T sub C sets the highest temperature at which liquid and gas can coexist. Stronger attractions, larger A raise T sub C, because the molecules hold on to each other more tightly and need more thermal motion to escape. Larger molecules, larger B, lower T sub C, because bigger excluded volume means molecules need more kinetic energy to behave independently again. So A and B do not just patch the ideal gas equation. They also tell us the conditions under which a gas can be liquefied at all. Before we wrap up, 5 traps worth rechecking. First, temperature must be in Kelvin, not in Celsius. Charles, Gay-Lussac, and the 1 over 273.15 extrapolations all need absolute temperature. Second, when energy or pressure is in view, average means RMS. The identity to memorize is 1/2 mv sub RMS squared equals 3/2 K sub BT third, specific heats are molar. C sub V equals F over 2R is per mole. Multiply by mass to convert to per gram values. Fourth, gamma depends only on F monoatomic 1.67, diatomic 1.40, nonlinear polyatomic 1.33. Read the table. Fifth, the two van der Waals corrections have opposite signs. A adds to P, correcting the attractive pull that reduces the measured wall impacts. B subtracts from V, correcting the excluded volume. The transfer point that ties it all together. Every formula in this chapter can be rewritten either per molecule, using K sub B and M, or per mole, using R and M. Pick the scale that matches the question, and the algebra stays clean. So here is what we built from the bottom up. The molecular model with its list of idealizations, turning a real gas into a tractable one. The empirical laws, Boyle, Charles, Gay-Lussac, Avogadro, and Dalton, all unified by the single equation PV equals nRT. The kinetic derivation of pressure, P equals 1/3 rho V bar squared, which is the same as P equals 2/3 E the three characteristic speeds, V sub MP less than V bar less than V sub RMS, and the full Maxwell-Boltzmann distribution they come from. Equipartition and the count of degrees of freedom, which gives gamma equals 1 plus 2 over F and predicts the specific heats of monatomic, diatomic, and polyatomic gases. And finally, the places where the ideal picture breaks, the van der Waals correction with its A and B, the mean free path, and the critical constants. The whole chapter is a single argument. The macroscopic gas laws are averages over a microscopic motion that we can write down, count, and predict. Whenever a formula in thermodynamics seems abstract, come back to one of these slides and ask which molecular average is doing the work. If this lesson helped the picture settle, the next ones will build on it. Subscribe to the Fiscribe channel to follow the series.